to talk about independent and dependent events. That's when two events occur, and we want to know the probability if, for an independent event, the two events that occur don't have any effect on each other. Okay, it'd be like rolling a dice and flipping a coin. It doesn't really matter what you get on the roll of the dice because the flip of the coin will still either be heads or tails. It doesn't matter. It's independent of each other. Dependent, however, is when they do affect one another. Like the most famous one is with the marbles in a bag. If you pull a marble out, let's say there's 10 marbles in the bag and you pull one out, all right, now you have, if you don't put the marble back in, now you only have 9 marbles left. So it's going to change the probability calculation. And conditional probability is a sort of dependent event where we're calculating the probability of an event like A, given that B has happened. Okay, and we'll talk about those in a second. All right, so first, how do we calculate the probability of independent events? Well, you calculate the probability of an independent event, like A and B happening, where A and B don't affect each other, by just multiplying their probabilities. Okay, so for instance, in example 1, one student in a class of 24 is randomly chosen to take attendance. What's the probability that the same student will be chosen 3 days in a row? Okay, so the probability that the student will be chosen the first day is 1 out of 24. The probability that he's going to be chosen at random the second day, again, 1 out of 24. So this is like if the teacher has popsicle sticks and she just pulls one out. And the probability for the third event, again, 1 out of 24. So when I multiply those all together, I get 1 out of 13,000. 13,824. Okay, so not so much big a chance of going 3 times. All right, the second one, during a high school track meet, each race consists of 9 competitors who are randomly assigned lanes 1 to 9. The probability that a runner will be in lanes 1, 2, or 3 in 3 races in a row. Well, he's going to be in either lanes 1, 2, or 3 out of 9 times the first race, 3 out of 9 times the second race, 3 out of 9 times in the third race. Okay, I can reduce all these down to 1/3 times 1/3 times 1/3. So that would give me, he has a 1 in 27 chance of being in one of those 3 lanes all 3 times. Okay, that's how we calculate an independent event. You just multiply each individual probability. Okay, in an dependent event, okay, where we're calculating, so again, independent, dependent kind of depends on whether one affects the other. So in the first one, you randomly select 2 marbles from a bag containing 15 yellow, 10 red, and 12 blue. So altogether, 15 yellow, 10 red, 12 blue, that's 37 marbles altogether. All right? And so if I want to know the probability of first picking a yellow marble and then second picking a non-yellow marble, okay, and the first time I'm going to replace them, so that makes them independent of each other. So the first time it would be 15 out of 37, okay, because 15 yellow out of 37 total, so my chances are 15 out of 37, I pick a yellow, times, and since it's independent, I pick again, I want a non-yellow marble, so that'd be these two. These two would be non-yellow, so that'd be 22 out of 37. And when I calculate that, I get 330 out of 1369. And I would reduce that if I could, but it already reduced, so they don't have any terms in common or any factors in common. All right, so that's with replacement. Okay, without replacement, which which means after I pick the marble, I'm just going to set it aside. I'm not putting it back in the bag. So the first time, I still have my 37 marbles in there. So I'm going to pick a yellow, and it's going to be 15 out of 37. But the second time, I now only have 36 marbles, and one of the yellows is gone. So my non-yellow is still 22, but this time it's only out of 36. So my probability is going to be 330 out of 1332. Okay? And my probability, does it make sense that the green one here is lower, that is higher, that I have a higher probability of picking if without replacement than I did back when we replaced it? And the answer to that is yeah, because here the probability that I was going to not pick a yellow went up because one of the yellows is gone. So now I don't have to worry about accidentally picking that one. So the probability of this happening after I pick a yellow is higher. All right, and the second example, if the teacher passes around a box with 10 red pencils, 8 pink, and 13 green, and you and the other 2 people in your group are the first to randomly select a pencil, what's the probability that all 3 of you selected pink pencils? Well, the probability it's without replacement, because obviously if you're taking a pencil, you're not going to just put it back. You're taking a pencil to actually use it. So we're going to calculate this without replacement. So the total, there are 31 pencils, 8 plus 13 plus 10. So the first person has an 8 out of 31 chance of picking a pink pencil. All right? But one of those pink pencils now is gone. So now there's only going to be 7 pink pencils, but only out of 30 total. Again, another pink pencil's gone, so now we only have 6, and we only have 29 pencils. So when I multiply all that together, I get 336 out of 26,970, which I can reduce to 51 out of 495. Okay? So that would be calculating an independent event and a dependent event. Dependent is without replacing it. Okay? So given this chart, let's talk about conditional for a minute. So I gave you all this chart, and just to do one more probability, the probability the randomly selected person has blue eyes. Well, 35 plus 9 is 44. So 44 people out of, and if I add up this whole row, I get 100 boys, and this is 100 girls. So 44 out of 200 people have blue eyes, or 11 out of 50. Okay? The probability that a randomly selected person from the chart above is a male with blue eyes. So we're asking for the probability that a person has blue eyes given that they're male. Okay? Well, the first thing you do is calculate the population what's the probability that it's actually given that it's male? Well, in this case, 100 out of 200, or 1/2 of the population is male. And so the probability that their eyes are blue, given the fact that they're male, well, 35 out of 100 have blue eyes, so that's 35 out of 200, or 7 out of 40 are men with blue eyes. Okay? Again, if a female has hazel eyes, would be probability that it's female, so that's 1/2. Hazel eyes is 41 out of 100 girls, so that's 41 out of 200. All right? So for and this would be written, probability of hazel eyes given that it's a female. Okay? All right. The last category we're going to talk about today is complements. Okay? A complement is the opposite of an event, or what everything beside that outcomes besides the one you're trying to talk about, or the positive event. Okay, and it's read A bar. So here, but it goes A bar. So if you think about, like, let's say I'm rolling a dice, and I want the probability of rolling a 3 plus the probability of not rolling a 3. Okay? Well, think about, what's the probability that I'd roll a 3 or not roll a 3? It would be 100%, right? So the probability of those two together would be 1, because remember, 1 is absolute certainty. So if I rearrange that a little bit, the probability of rolling a 3 is equal to 1 minus the probability of not rolling a 3. Right? So we call not rolling a 3, it's the complement. So this is the probability of A, and it's equal to 1 minus the probability of A bar, its complement. All right, so let's try practice a couple of these. All right, so if we're rolling a 6-sided die, and there are 36 possible outcomes, find the probability that the sum is not 4. Okay, so we're looking for the probability of not getting 4. Okay, well, there's a lot of that. I mean, not getting 4 means I could get 2 and 3 and 5 and 6 and 7 and 8 and 9 and 10, 11 and 12. It means I can get a lot in a lot of different ways. So I don't really want to add up all the probabilities of not getting 4. So instead, sort of like a shortcut, I'm going to use the complement. I'm going to use 1 minus the probability of actually getting a 4. And those are equal. Because 1 minus the probability of getting a 4 would be the probability of not getting a 4. All right, so what are the ways I can get a 4? I can get 2 and 2, 1 and 3, 3 and 1, and that's it. So there are 3 ways out of 36. So the probability of getting a 4 is 3 out of 36. And so 1 minus 3 out of 36 is 33. 36. Or if I reduce that, 11 twelfths. Okay, so 11 twelfths is the probability of not getting a 4. Okay, the sum of our dice is greater than or equal to 3. So if I want the probability that's greater than or equal to 3, I'm going to do the shortcut and say, okay, I want 1 minus the probability that it's less than 3. Because gosh, if you roll 2 die, what's going to be the only thing less than 3? It's 2, right? So this is going to be 1 out of 36. The only thing that's less than 3 is 1 and 1. So the probability of getting greater than or equal to 3 is 1 minus 1 over 36, which is 35 over 36. Okay? So that's a complement. You use a complement at the opposite of what you're trying to find to usually do like a shorthand or shortcut way to get through kind of go to the back door and get to the problem that you're trying to solve.